Today I'm going to introduce the paper of research of MNC plus M quiz with markup form multi-day service process. And this is the introduction. A service interruption is a common issue in many real-world systems. Like in manufacturing, interruption can come from machine breakdowns or scheduled maintenance. And in transportation, they might be caused by traffic accident or vehicle structure. And in contact center, they can result from the private servicing of higher priority customers. This interruption don't just pause operation, and they lead to a serious like delays and system congestion and reduce service rate, and even the customers abandonment. And in this research, we meant to analyze how this service interruption affect the overall performance of queuing systems. And to make this discussion more relatable, we use the traffic flows on a roadway think as our current example throughout the study. And this is the model, and we represent a road segment as a queuing system with C identical servers. In this analogy, each vehicle is considered a customer, and each occupied row space acts like a server. And when a vehicle enters the segment, service begins immediately. This corresponds to the car starting to travel through the road. And the service is considered complete when the vehicle exits the segment. As shown in the figure below, we model this using a tilting roadway stick, where the length of the road and the number of vehicles determine the total service. And now we talk about what happened when the incident occurred on the road segment. And we assume that the random service interruption, such as an accident or a sudden breakdown, will reduce the service rate and in other words, the vehicle moves very slow. And during the interruption, there are two key assumptions. First, all vehicles already on the road remain in the system. That means we don't remove or clear any cars from the segment even when the service slows down. And second, new vehicles continue to arrive as usual. As shown in the diagram below, the model is built on a markable long-dated service process, and it used different states like normal and closure, with the transition controlled by the forward and reverse brakes, denoted as the F and R. And you can see when you have virtual and your meal will become long and it will be slowed down. And when you have a repair state, you will come back to the normal one and get the normal meal. And here we explain the key of assumption behind the system state management. And first, we assume that interruption, vehicle arrivals, and service time and clearance time are all independent. Second, we assume that service rate decrease during the interruption, for example, when the traffic slows down due to an incident. And finally, we assume that the service time follow an exponential distribution. This means that when any introduction and the remaining service time for each vehicle have behaved as if it starts fresh. This is because the exponential distribution known as the memories. And this helps the maintain mathematical gestability while allowing us to model the relative service disruption. And this is the result of the case where we have a single service system that is C equals 1 and no customer abandoned, meaning the theta and theta plum equals 0. And on the left is my simulation result under the different combination of virtual and repair rates. And on the right, we can see the physical values from the original paper. And as we increase the service rate, mean the expected number of the customer in the system decrease, which is consistent across all FNRs. And this figure shows the expected number of customers in the system with different value of abandoned rates theta. And when the theta increase, the meaning of the customer are more likely to leave the is. And you can see when the theta increase, the customers are more likely to leave. And the average number of the customer in the system decreased. And this is the result of the arrival rate lambda equals 1, and we assume that mu plum equals theta plum and mu equals theta. And you can see when the mu increase, the mean of the number of customers in the system will decrease. And this is left one is the simulation, and the right one is the papers. And this is the result of lambda equals 1 and mu plum equals theta plum, and mu equals theta, and mu equals 10 mu plum. And we can see the number of the customers in the system decrease while the service rate increase. That the same time series interruption cause the value of F and R to have more significant effects on the exact number of customers in the system. And this is the conclusion. The paper analyzed the MNSPC twin model with microphone based service process. And the interruption like high F and low R cause the greater system congestion and stronger sensitive to interruption the parameter. And the exact number of the customer in the system decrease as the normal service rate will increase. And this is my presentation.
So you have the simulation results already and compare to the results in the paper, right?
Yeah.
Left hand side and right hand side. Left hand side is yours.
Yeah, this one.
So maybe except one figure you don't have the pretty much result. For the other seems to be okay, right?
Yeah.
Okay. Alright, so I think you can recheck how to have the better accuracy for one of the figure. You can see one of the figure you have a shift.
This.
Yeah, maybe
Yeah.
this one.
And
So why and how you can avoid the inaccuracy? Maybe you can reconsider how to do that.
I have think about why. And in the papers, this simulation didn't tell us the arrival rate of this or the C is equal to.
So only this one?
Yes.
Okay.
And
As for the others, you have the
yes.
arrival rate.
The arrival is equals to 1.
Oh, okay. But that one you don't know.
Yeah, they didn't tell us the arrival rate.
So you have your own setting.
Yes, I tried my best to get the arrival rate.
So maybe you can try to guess which value should be set.
Yes.
Okay. All right. Thank you.